Decidability is you can if you able to form your problem in such a way that it can be reduced to either true or false problem, then you can say that a particular problem is decidable. And in forms of algorithm, it's a different thing, that computability, that you have to compute a definite function on which a certain complexity will be attached to it. Okay, that is the core difference between. So I'll again merge these two concepts. And again, one single point that I've told you, that for a single instance, for a single instant, any problem is decidable. And I have given you the example that to check out ambiguity, that there is no algorithm. So decidability is when you can form an algorithm, when you can build an algorithm for a particular problem, then you can say that the particular problem is decidable if you're not able to form any algorithm, or your algorithm is taking more time, that is in the form of exponential exponential complexity, then we can say that your problem is not decidable or undecidable. Okay, so I'll take this example that for a single instance, this ambiguity problem is decidable, but if I exceed, or if I include more grammars in the domain, this particular problem will become undecidable. Okay, so that is the only difference. And actually there are two important things that I also want to tell you, that how to prove that a particular problem is undecidable. Okay, so first step is, if a particular problem, suppose this is a P1 problem, and if there exists an algorithm that can reduce this problem, suppose that can reduce this problem to another problem, that is your P2, and this, for this P2, a halting Turing machine can exist. Okay, so suppose this is a particular problem, and then but you can convert this problem by following a particular algorithm into another problem, that is your P2. And for that P2, if there is a halting Turing machine, then you can say that your P1 is decidable. Okay, so that one condition is there, that if P1, there can be, suppose there are many problems that at the first instance seems undecidable, but if there is any kind of algorithm exists to convert, by saying algorithm, I mean that then there is only that there is a time complexity of like n square out of that, so that can convert this problem to another problem. And for that problem, if there is a halting Turing machine, it means that it is decidable. Okay, so if it is very simple, that you can say that if there is a halting Turing machine, it means that it is decidable. If for a halting Turing machine, it means that there is an algorithm. Okay, so I have already told you this one. Any doubt? Okay. Okay, so the first step is that okay, so if there is any particular problem exist, and for that particular problem there is an algorithm, that it particular problem can be converted into another problem for which a halting Turing machine exists, then you can say that this P1 is decidable. Okay, so if that is called your the power of reducibility. Okay, so this particular step is called reducibility. Okay, in the similar way, there is another thing that for particular problem P1, it is already proven that this particular problem is undecidable. Okay, so it is already proven, so there exists a proof that says that this particular problem P1 is undecidable, and you have taken an algorithm and converted into P2, so that P2 will again always be undecidable. Okay, so if it is already proven, there is no way that you can reduce this problem to another problem and that problem can be a decidable problem. Okay, so make sure that is if it is already proven that P1 is undecidable, and you convert or reduce this problem to any other problem, that there is no way that P2 will be a decidable problem. Make sure. Okay, so there are two important things also. If you are in the topic of decidability, you just have to know these two definitions. Okay, so this is just not this is just an introduction of it. There are many questions in competitive exams that are asked on only based on these two things, only these two statements. There are many questions exist there. Okay, so now another theorem that I want to tell you about is something called a halting Turing machine. Okay, so you also already know what is Turing machine halting problem. Okay, so for a particular problem, if a Turing machine halts, you can directly say that a particular problem is recursive, and if it does not halt, it may there are two main problems. If a particular machine halt and say yes or no, then your particular problems become a recursive. If a particular problem either it can halt or say yes, or it can either say no, or it can fall to a infinite loop. For that thing, we say this is your recursive enumerable language. Okay, so halting problem says, okay, so I'll again just let me again share if I have a PPT. I think I've written this problem. Just wait a second. Okay, this is your halting problem. Okay. Okay, so this halting problem says that a Turing machine, if it is inputted with a particular string, so the problem is, does the Turing machine finish computing of the string in a finite number of steps? Okay, the answer must be either yes or no. Okay, so if you are able to tell it, this is your halting problem. If you are able to tell yes or no, then say that you can say that your Turing machine halts. Okay, at first we will assume that such a Turing machine exists to solve this problem. Okay, so first it is proof by contradiction, and we assume that for every problem there is a halting Turing machine, and then we again, this is a contradiction problem, and we will call this Turing machine as a halting Turing machine that produces a yes or no in a finite amount of time. If the halting machine finishes in a finite amount of time, then the output comes as a yes, otherwise it's a U. Okay, so following is the block diagram of the halting Turing machine. There is input string, it will either say yes or no. So halting problem, it itself is a undecidable problem. Okay, so that is one of the most important thing that I want to tell you, that halting problem is undecidable. Okay, so again, I have given you an example of customer care, that either you will either it can be a halting Turing machine, or I cannot directly say that my Turing machine will halt at some time, or it will keep going. Okay, so that is why it's a very important thing to keep just remember this part. Also, it is also already proven that Turing machine halting problem is a undecidable. Why it's a undecidable one? So suppose okay, so I write a theorem also. The theorem says if the halting Turing machine is, now I'll prove it by a contradiction. Okay, so again, this will be again based on the previous proof that I've already told you. So if the halting Turing machine so I'll say was, yeah, is decidable, then it's a proof. In this statement, it's a proof. Then every recursive enumerable language would be recursive. So that itself is a self-explaining statement. Consequently, I can say the halting problem is undecidable. Okay, so I'll explain you what is the meaning of that. Okay, so it says that we have already proven that there is at least one recursive enumerable language that is not recursive. Okay, so based on this statement, I have already proven that there at least exists a one problem that is recursive enumerable, but that is not a recursive language. So that is the problem. Okay, so if this is already proven step in the previous lecture, I have already told you about this. Okay, so there is at least one problem that is recursive enumerable but not recursive. Suppose that problem is this. Okay, so it is saying that if halting Turing machine is decidable, so it is saying that if halting Turing machine is decidable, if it is decidable, then every recursive enumerable language, this one, becomes a recursive language. But it is not true, because we have already proven that there at least one particular, there at least one problem that exist, there it's at least one problem exists that is recursive enumerable but not recursive. So based on this statement, I am saying that consequently the halting problem becomes undecidable. Okay, so this is very important part that you remember. It's a very important step. Okay, so just keep this in mind that your halting problem, that when will your Turing machine will stop? I cannot answer that. That is undecidable problem. Okay, so in the similar way, there is some problem like I've already told you that epsilon is accepted by a Turing machine. This is also undecidable problem. Okay, so if you want to see more problems, again, if you remember, I have shared with you the decidability property chart earlier. So just take a look. There are many problems, and in that problem you will already find that for Turing machine, for recursive language, all of the problems are undecidable. Okay, so if you check it, you will find it. There is another thing that this is your post correspondence problem that is already given in your syllabus part. So again, you will not understand here what is exactly it's saying. The post correspondence problem is introduced by ML Post in 1946. It is also an undecidable problem. Okay, so keep in mind, this is also an undecidable problem. The PCP, so the problem is given like this. Okay, so I'll tell you with the example that will be more clear. It is saying that suppose there are one variable m and there is another variable n, and it is given the strings are given like this. Okay, so I have to arrange this string in such a way that something like if suppose it is given to this table is given to us. Okay, so I have to arrange our string in such a way such that from strings from, if it is denoted by x, and okay, so I'll just give the solution to you. Okay. Okay, what I'll do, I'll take another example. It's a little bit difficult one, so I'll take another table. So it's suppose there is W1, W2, W3, and for W it's A, AB, and BBA. Just taking example, I have written the example W2, W3, and W3. It is BAA, AA, and BB. Okay, so I have to arrange this W1, W2, W3 in such a way that I get the same string. Okay, suppose I arrange this as W1 and W2, and suppose you can repeat any string any number of times such that the string that you get from here is equal to the string that you get from here. Okay, so I have arranged in 1 2 3. So for V I have also want to arrange it in V1, V2, and V3. Okay, now see, it is A, it is AB, it is BBA. For V, it is BAA, it is AA, it is BB. Okay, so the string is not equal, so that I cannot say that it is equal. Try another step, that W2, W1, W3 is equal to, it should be equal to 2 1 3. Again I have to write the same thing here, 2 1 and 3. Okay, so for W2, W2 is AB, W1 is A, and W3 is BBA, and for W2 BAA, W1, sorry, W2 is AA, W1 is BAA, and W3 is BB. Okay, again you check it, the string are not equal, but so you can also try like W2 2, W2 1, and W3. Okay, so for the corresponding, you again have to take 2 2 1 3, same sequence, W2 V2 V2 1 V1 and V3. Okay, so if you check W2 it is AB, but for W2 it is AA. Again you can say that string is not equal, so it is definitely sure. Another can be, another one can be 3 2 3 1. Okay, so this is the solution to this one. Okay, so W3 and, okay, check this one, W3 BBA, W2 AB, W3 BBA, and W1 A. Okay, so now check this, W3 BB, W2 is AA, W3 is BB, and W1 is BAA. If you check it, both the strings are equal. Okay, so the problem is such a way that you will given this particular table, you will given a particular table, and you have to find a particular string. You have to arrange, suppose this is the sequence 3 2 3 1. So I find the sequence such that this sequence when applied to another what you say, another example, it will result in same string. So that is your problem. Okay, so suppose this is a string given to you, this is, you can consider this as x1 x2 x3, you can consider this one y1 y2 and y3. Okay, so whatever you arrange, so here if you see the solution is given as x2 1 and 3, and 2 1 and 3. So it should be same, 2 1 and 3, 2 1 and 3 here, and the string will be same. Okay, so that is your post correspondence problem, also referred to as PC problem. It is also based on the same thing. Okay, so this with this I think all your syllabus is completed, and I just share you with the syllabus part also. So only I have given you a self topic of this particular topic of just let me show pumping lemma for context free grammar. Okay, so this is your self topic. All the topics have been covered by me in the class, or and if you check Turing machine, I think you know what is the holding problem now. It is an undecidable problem with the theorem that is already done. Okay, so Turing enumerability, acceptability, and decidability. Again, it comes under recursive and recursive. With that, regarding to that, I also told you like two important theorems that is very important in Turing acceptability and decidability. We all know the I already shared you the table also you can find in like week 7 or 8 classes where we are discussing the regular grammar properties. I've shared two particular charts for this one. Okay, so you can refer to there. And if you say your CO3, that is apply the concept of recursive and recursive enumerable and design efficient Turing machine. So we have designed very efficient Turing machines. If you see the Turing machine acting as an adder, as a separator, we have done this. And recursive and concept of recursive and recursive enumerable languages, I have discussed very core and very essence of this recursive and recursive enumerable languages, as well as the concept. If you know about a particular two theorems that represents a very deep part of recursive and recursive numerable languages. Okay, so keep this in mind. And we already know you already know about the context free grammar. We have designed a push down automata, and I think for the first you are expert in that also. So NFA, DFA, and you are I think our all the course learning objective have been successfully completed. I've covered all the parts. Still, all the videos will be again uploaded in the YouTube list, as well as it is already recorded and it is uploaded at the end of the lecture. Okay, so if you have any doubt, just let me know, or I can share you the link of the lecture. Okay, so another thing that